Good morning. This is Mr. Reynolds, and what we want to explore today is something called electron dot notation. Okay, and then after that, we'll look at some Lewis structures, which is basically the same thing, but it may look like foreign words to you right now. But as we go to this next slide, you already know how to represent these things really, really well. For example, carbon that you've done Bohr models with the carbon. It's all based on that. Since you know how to do that, then this will be a nice form of doing this. Carbon, 6 protons, 6 neutrons, 2 on the first shell, 4 electrons on the second shell, and this is going to be the key. Of course, this whole periodic table is set up for valence electrons, and that's what we're after. So another way of depicting this, since where it will show carbon and then dots around it. So again, electron dot notation. It's just going to be representing the valence electrons. And on this one, they will spread out. Okay. So one on each side. And there we have it. Okay, this is the electron dot notation for carbon. Okay, let's do electron dot notation for beryllium. Okay, and what you know about it, just in the back of your head. Oh, that's 4 protons, 5 neutrons, 2 electrons on the first, 2 electrons on the second shell. So we're going to use the valence electrons only. That's what we're going to do. Non-metals are going to lose their valence. Non-metals are going to gain to their valence shell. So again, the whole chart is set up for valence electrons. Okay, so beryllium is going to be just 2 electrons together. 2 electrons together on it. Okay. Let's look at oxygen. Oxygen is 8 protons, 8 neutrons, 2 shells. We can stay in this second row of the periodic table and be in real good shape on this. So anyway, electrons, it's got 2 electrons on the first, 6 electrons on the second shell. So electron dot notation for oxygen is the symbol oxygen. And we've got the 4 sides. We're going to put a pair of electrons, one electron, 1 electron. For my 6 electrons, I need to spread them out, okay? And it may vary some depending on what it's bonding to and how it's bonding. They'll let them be varied around some. So here's another one for oxygen, okay? Or we might see oxygen with 6 electrons. And you can spread them all out first if you want to on the 4 different sides. There's 4. Oh, it needs 2 more. Let's put 1 here. Let's put 1 there. Voila, there you go. There's the 6. So all of those are different representations for electron dot notation. Let's do nitrogen. 7 protons, 7 neutrons, 2 shells, 2 electrons on the first, and it's in tall column 5 valence electrons. And these are the ones that I need for electron dot notation. Okay, and you've picked up so far, electron dot notation means just individual atoms. Okay, so nitrogen, and it's got 4 sections, and the sides actually represent an S, a PX, a PY, and a PZ. Okay, that's what the 4 different sides represent. So S, side, those 4 sides. Oh, I need a 5th electron. Oh, let's put it there. We know we how to fill that S up anyway, right? But anyway, there's 5 electrons. And like I said, depending on what it's bonding to, these can be moved around some as need be. Okay, this is another acceptable thing for nitrogen. We might see nitrogen with 2 electrons there, 1 in each of those other 3 positions. All those are good electron dot notations for that. Let's go to the next slide. This is getting a little messy. Let's do fluorine. Okay. Fluorine, we'll do a couple more of these. 9 protons, 10 neutrons, 2 shells, 2 on the first, 7 on the second. Now I need 7 valence electrons for electron dot notation, 4 positions. Oh, okay, usually we fill the cup up at the top first of all. We work our way around clockwise. Okay, and there's my 7 valence electrons. Okay, Let's do oxygen, and that'll be it. Well, we did oxygen. Let's do let's do a noble gas. Let's do all noble gases except for helium, and in a stable octet. Okay, and we'll come back to that one. So 10 protons. Helium has 10 neutrons. 2 shells. 2 on the first, and it's noble gas. Stable octet, so 8 electrons on the third shell, on the second shell, and that works out. Okay, I need these 8 electrons, these 8 valence electrons around the neon. Well, 4 places. Okay, there's 1, 2, 3, 4, 5, 6, 7, 8. Okay, there's my 8 valence electrons, and this is the electron dot notation for neon. Electron dot notation for fluorine. Electron dot notation for oxygen, 6 valence electrons. Nitrogen, 5 valence electrons, 2 and 5. Okay, 2 on the first, 2 in one place, 3 in the other. There's my electron dot notation for oxygen. Okay. Carbon has 4 valence, and like I said, we'll put 1 in each of those 4 different locations. There's my electron dot notation for carbon. Okay. Okay, now we want to look at some Lewis structures. Okay. And a Lewis structure, it's really kind of a play on words. It's just it's 2 or more of these atoms bonded together. So we call it electron dot notation, even though it is that same style. Okay, we call these Lewis structures. And for example, let's do molecular hydrogen. Okay, hydrogen is, here's the electron from this hydrogen, here's the electron from that hydrogen. We'll make it an X, so I can see where those 2 electrons are. Okay, if you need to backtrack just for a second, get your thoughts together. You knew hydrogen has 1 proton, no neutrons, 1 shell, 1 electron on the first shell. Okay, and well, that's how you knew that one from before. Let's do molecular fluorine. Again, Lewis structure, since we're putting 2 or more of these together. And each fluorine had 9 protons, 10 neutrons, 2 shells, 2 on the first, 7 on the second. So I need 7 electrons around, 7 valence electrons around each of these fluorines. So, and it's going to be single bond. So this fluorine, let's give it 1, 2, 3, 4, 5, 6, and 7. Okay, bonded together. 1, 2, 3, 4, 5, 6, and a 7th one. Okay, so these 2 electrons are being shared by each fluorine. So we have a single bond between them. And we could do it like this. Okay, that's our next step. This dashed line we know is 2 electrons, extremely strong covalent bond. Again, if we're bonding molecules together, this is all nonmetals to nonmetals. Okay. This is, let's look at this hydrogen again really quick. Well, let's say it's one electron on the first shell, and we did this style a little bit before. Okay, all right, well, these Bohr model, overlapping Bohr models, this works pretty well for single bonds, but it doesn't work so well for double bonds or triple bonds. And so each of these styles has some advantages. The electron dot notation works out pretty well for double bonds on it. Let's do another substance that you're breathing in right now is molecular oxygen. In fact, you're breathing in about 20%. Everything, every gulp, every breath of air you take in is close to 20%, about 18 something percent of oxygen. Okay, and the thing is with oxygen, it is double bonded, real strong bonds on this. We can it's tough representing that with overlapping orbitals, with overlapping Bohr models. But with electron dot notation, we can do that pretty decent. Okay, we got oxygens next to each other with a double bond. We've got a pair of electrons here, pair of electrons there. Okay, and So these circle electrons go with the left one. Okay, so let's finish this out here. 1, 2, 3, 4, 5, 6, and then a 7th and an 8th one. Okay, this oxygen is donated electrons. Let's make those X's. There's 6 of them, and then a 7th and an 8th one that are also being shared. So here's my double bond with those two. Okay. The other thing that you're breathing in is molecular oxygen, and that's actually a triple bond. Okay, that's why we inhale, and it's close to 80% what you're breathing in right now and breathing out. So we breathe this in, we breathe this out. These triple bonds, your body's not going to be breaking those down. We need nitrogen, but we don't. As much as we breathe in, we don't get any of it from the air. Okay, we breathe that back out. We have to get nitrogen in through our diet as nitrates and nitrites that you learned some before. Anyway, representing this with triple bonds, which would be really, really tough with overlapping with the overlapping orbitals, with the overlapping Bohr models on this. So, but with this, we can do this okay on it. Okay, so there's nitrogen, 1 electron from the left one. We're going to do triple bond here, right? Where it's sharing 3 sets of electrons. 1, 2, 3. So each nitrogen, so that's 6 electrons that this one thinks it has. We'll give it its other 2 electrons here. That's its 7/8 electrons. This one, it's got 6, 7, 8 electrons being shared. Wow, really, really, really strong bond between this. Okay, we're not going to be breaking that down. Okay, and we're going to do, actually, we got one more slide. Okay. Okay, let's do this one more. We were working on a lot of some organic compounds, hydrocarbons, carbon bonded to carbon, and then hydrogens around it. Okay, we were doing that. So let's look at this carbon to carbon bond. Okay, let's do okay. A carbon bonded to another carbon. Here's 1 electron from the left carbon, 1 electron from the right carbon. Hydrogens around it, 1 electron from the carbon, 1 from the hydrogen. 1 from the carbon, 1 from the hydrogen. 1 from the carbon, 1 from the hydrogen. Let's start making the hydrogen X's. Let's do that. 1 electron from the carbon, 1 from the hydrogen. 1 electron from the carbon, 1 from the hydrogen. Okay. The carbons will bond, strong bond between those. And let's do electron from the carbon, 1 from the hydrogen, 1 from the carbon, 1 from the hydrogen, 1 from the carbon, 1 from the hydrogen. We're done. Let's go back and change these to X's over here so I know that that's coming from the hydrogen. All right, this would be example of, this would be, oops, sorry, I was going to say pentane, my bad, propane. Okay, pure hydrocarbon, all single bonds between them. This is actually, and again, since it's more than one element, this is going to be Lewis structure. So just basically a change in name in what you're doing. Okay. All right, this will probably help with some of the questions that you need to answer. Thank you very much.